Extreme physics.
All right, as you can see, I'm not here today. Well, I'm here, but I'm not there in your classroom. So today we're going to do a little virtual sort of lesson. I'm going to give you a problem. You're going to work on your whiteboard. You should all have your whiteboards. My replacement teacher will pause the video. When I indicate, I'll give the signal, and they'll pause the video, and you'll work it out on the whiteboards, and then we'll come back and we'll talk about it a little bit. Well, at least I'll talk about it to you. So we have a problem. A lab cart with an initial velocity of 50 centimeters per second coasts to the left and is accelerating at a uniform rate of 8 centimeters per second squared to the right. How long till it reaches its farthest point from the start? All right, well, we're going to use some of those new kinematics equations that we started working on yesterday. And we're going to take a look at a video. So let's take a look at a cart like this that I recorded a while back. Let's take a look at that right now. Relative to our problem, in the video, when does the problem begin? When is the cart coasting? All right, when I'm pushing it, you can see that it is not coasting, it's being pushed, and it's actually accelerating up the ramp, which is to the left. Now, they said in the problem, it's a constant acceleration of 8 centimeters per second squared to the right. So the problem must begin after it leaves my hand. So we'll start that there. All right, we should set up a coordinate system. What should be our zero position? It's not critical. You can solve it no matter what you call zero. But we might as well, since we want to know how far it goes up the ramp, might as well set 0 at the beginning. And then when it gets to the end, it'll be up like that. So I would set up a coordinate system like this. I will start this right here. Our cart will start right here. And there's our cart. And it is going to accelerate, and it's going to reach its farthest point. I will call this T0, and I will call this T1. That's the farthest point. And then they said the whole time, this thing's accelerating. Which way is it accelerating? They said it was that way. 8 centimeters per second squared. In the video, when does the problem end? Well, of course, it ends when it gets to the end there. And what happens then? What happens at the end of the problem? What happens at T1? What is V1 at T1? What is the velocity of the cart at T1, at that farthest point? Well, V1 equals 0. It stops. Right? Is it going up? It's going up, and then it stops. And that's going to come back. So that's the farthest point where it stops. What's our initial velocity? Is our initial velocity 0? Is our initial velocity, I will get a lot of that. Is it moving fast in the beginning? Is it moving slow in the beginning? Is it not moving at all? Well, let's take a look. If we take a look at our motion diagram sort of thing, we can see that the V0 is high, and in the problem they actually gave it to us. It's 50 centimeters per second in this case. But we should understand, even if they didn't give that to us, that if you're pushing something up a ramp like that and it's sliding back later, that when you release it, it's going as fast as it's going to go. So let's set up the problem.
Pause the video now.
V0 is going to be 50 centimeters per second. Now, is that positive or negative? Well, it's in that direction, and we remember in our math class, this way is positive, and that way's negative, and up is positive, and down is negative. We don't go up and down in this problem, though. That's why. This is strictly a horizontal problem. When does our problem end? At V1, and that equals 0. So we need, by reading the problem, we had to realize that this problem ends at 0. If you couldn't do that, you really can't solve the problem. So that's the tricky part, right? All right, V1 is 0, and they gave us acceleration is that way, so that's positive. Oh, this is negative velocity. I didn't put that in there. At negative velocity, that way, and positive acceleration. And what was the question? How long? Now, long sounds like a distance, but that's actually time. It's the way we, in English language, we often express that. We say, how long until the football game starts or something like that, you know? Well, you know, if we look on our reference table, we have something that looks like this. V final equals V initial plus AT. So we're going to use kind of that equation. Let's use variables that we did, though. V1 equals V0 plus acceleration times our time interval. Rather than CT, I just put delta t there to remind us that it's a time interval, it's not a time. I'm going to solve for time. Delta t equals V1 minus V0 all over A. I would always recommend that you do this and then plug the numbers in as the last step. All right. What's 50 divided by 8? We had centimeters go away, and 1 of the seconds go away. 1 over seconds in the numerator, that becomes seconds. 8 seconds. It takes 8 seconds. Next question. What will the location of the farthest point be? Basically, they want to know what is x1 equal.
Pause the video now.
I keep forgetting to put the direction on my velocity. My V0 is this way. That's negative. That's negative. V0 is 50 centimeters per second to the left. All right, I think we're going to use squarey. Squarey says V final squared equals V initial squared plus 2AD. Now this is a displacement. I'm going to write this a little differently. I don't like this. I'm going to say V1 squared equals V0 squared plus 2 acceleration delta x. All right? Remind us we have a motion from that way to that way. We have a negative displacement, I believe. We go from here to here. We're headed in the negative direction. Got to put that in there. All right, what do we want? Want x1. We want to know what this negative displacement is, really. All right. So I have V1 squared equals V0 squared plus 2 acceleration x1 minus x0. That's what delta is. I should have said that. From 0 to 1. All right, just solve the algebra. Just doing some algebra. All right, what do we got? That's 0. Just plugging the numbers in. I got them all here. I got to do is just plug and chug at this point. I think this comes out to 156 centimeters. Let's see, we're going to have second squared is going to go away because we had second squared here. We have centimeters squared over centimeters. That's going to go away, and we're going to just end up with centimeters. Now the difficult part. Draw stacked graphs of position versus time, velocity versus time, and acceleration versus time for this motion. First step, plot some points. Plot some points where, if you know the position in the beginning, velocity in the beginning, acceleration in the beginning, I will give you a second to do that.
Pause the video now.
All right. After you plot the point, you need to look at it and say, at that point, what does the slope represent? What does the slope represent? We don't interpret this slope. you should be writing these down too. Slope equals delta x over delta t equals velocity. The slope of this graph represents, let's see, what does it represent? Oh, it represents acceleration. The slope of this graph doesn't represent anything that we study in this class. All right. Well, our cart started here. We said we were going to call that 0. Starts here. What's the slope? Slope is velocity. What's the velocity? Well, it's actually 50 centimeters per second that way. So the velocity initially is minus 50 centimeters per second. Might as well put that here. So right there, minus 50 centimeters per second. And that's as fast as it's going to go. So why don't we make that a big velocity? It's right here. It's right there. All right. What's the slope? The slope is velocity. The velocity is negative 50 centimeters per second. So the slope is negative 50. That's the slope at that point. All right? That's the slope of the line. And the slope is negative 50 centimeters. Now, I can't tell it's 50 centimeters per second, but it is. It's negative. All right. Velocity is here. And in this class, we have a constant acceleration. The whole time it's going to roll up here. We have an acceleration this way. All right. So we had, and that is a positive acceleration. So it's 8 centimeters per second squared. The beauty of the acceleration graph in this class is that the slope is always constant because in this class, our accelerations will be constant unless they change abruptly. So this is going to be a steady, it said right throughout the problem, it's the same value. Beauty. Now, the slope of this represents acceleration. What's the acceleration? Positive 8 centimeters per second squared. Slope is acceleration. Acceleration is a positive 8 centimeters per second squared, so I need a positive slope. Does this thing ever, well, what's its velocity at the end? I will call this x1. This was x0. v1 equals 0 when it gets to the end. So our velocity at the end is 0. This will be the end. This will be the end. Well, anyways, let's put it here for now. And the slope's going to remain constant. So we're going to go zoink, like that. It's not going to go positive. It's going to stop. In this problem, it stops. If we continued it, it would continue to go, it would start going positive, but that's not part of this problem. All right. Let's go back to here. Where does it end? Well, it ends in the negative direction down here in time, and it's like this. What's its velocity at the end? 0. 0. So it has a 0 slope. All right. So this must be a curve. If it gets to be 0, it's the only way we can connect those. All right, looks like that. The rate of change of position is constantly changing because it's accelerating. We have a constant change in velocity here. And this slope, of course, slope equals 8 centimeters per second squared. That's the slope. This slope is 8, a positive slope. That looks positive to me. And there we go. Okay, that's where it's a 0 slope. That's where the velocity is 0. All right. All right, let's try another problem. A lab cart is released from rest. Oh, this one stopped. Why don't we treat this? Could we use this same video? Maybe. And coasts to the right and is accelerating at a uniform rate of 8 centimeters per second squared to the right. How long until it travels 156 centimeters? All right. Well, sure. I think we could use the same thing. We're going to start the problem here, though, because it starts from rest. That's at rest. I'm going to call T1 equal to 0. And then how long till, well, this is it turns out this is going to be, I'll call this X2. It's going to be going this way. All right. So we're going to use the same video, only we're just going to start it later. And then it's going to roll to the end. All right, let's see what happens. How long until it travels 156 centimeters? Let's see what we got.
Pause the video now.
I think we can use the same video, but since we're starting a new problem, why don't we just, so we don't get confused. Why don't we start it here? We'll call this our new X0, and we're going to end it when it rolls down to here. And this is going to be 156 centimeters. And this is going to be 0, obviously. V1 is 0. Acceleration is 8 centimeters per second squared. X0 is 0. X1 is 156 centimeters. How long? Delta T. All right, how long is it going to take to go from 0 to 1? All right, I think we can do that. Let's call this V0. Let's call that V0. In your reference table, El Grande looks like this. D equals VIT plus 1/2 AT squared. Let's see. We have this. Do we have a V initial? Yeah, we got that. And we have that. All right. And we could solve for time. We're going to have to solve a quadratic. Well, that's would be unfortunate. But luckily, V initial is 0, so it's an easy quadratic to solve. And it turns out El Grande will become El Nino because this is 0 equals 1/2 AT squared. All right, so we got something like that. All right, that's easy to solve. That's a quadratic that I can handle without doing fancy mathy stuff. I'm going to say delta x. I'm going to replace that with delta x. More meaningful to me. 1/2 a delta t squared. All right, delta t equals the square root of delta 2 times delta x all over a. And of course, that's plus or minus, but we're not dealing with negative time here, so that's this is going to be positive. We're taking the positive answer. All right, how long did it take? To come down. What will its velocity be when it reaches 156 centimeters? What will its velocity be?
Pause the video now.
We'll use squarey. Squarey, V final squared equals that. All right, let's take a look at squarey. Because we have this. We have V initial. We have acceleration. We have 2. We always have 2. And we have the displacement. Good, 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 good. Don't want that. V1 equals question mark. All right, so all this stuff's good. We want V1. Generally, if you can avoid it, don't use an answer from a previous question to answer one of these, because if you made a mistake, then you make another mistake, and your answer might be unreasonable because of the previous mistake, and you can't judge your answer. So if you can, only use the information they gave you. Don't use a solution from an earlier problem. Sometimes you have to. But if you don't have to, don't do it. V1 squared equals V0 squared plus 2a delta x. All right, I'm going to put it in my more useful square. I forgot the square. More useful format, like that. And instead of this Regency stuff. All right. And that should come to 50 centimeters per second. Now, it's plus or minus. We have to figure out, is that going to be plus or minus? Well, it's that way because math doesn't tell us that. It just tells us it's plus or minus. We have to look at the context and say, oh, that is indeed in the positive direction to the right. All right, let's draw our graphs.
Pause the video now.
All right, so it started at 0 again, because we defined that as 0. It started off with a 0 velocity. And the acceleration, again, is constant. It's that way. It's positive. The acceleration graphs very often will be quite easy in this class because they'll be constant or 0, constantly 0, or something like that. All right. We had a 0 velocity, so therefore, I'll draw the slope in red. 0 slope. 0 slope. And it's going to make it down to 156 positive. So it's going to make it up to here. At that point, it's going to have a positive velocity of 156. This will have a slope of 50 centimeters per second. So, all right. So the only way we would be a curve, sort of like that. Oh, shouldn't have gone low there. Should have gone, kind of flat here. Slowly gets speed and goes up like that. All right, what's our acceleration? It's a positive 8 centimeters per second squared. So we need a positive slope here. And then later, the velocity is that way. It's positive, it's up here, and this still has the same slope throughout. That is linear, like that. And finally, we had our acceleration. All right, that's what our graphs should look like. So hopefully this graphing stuff started to make sense. Always take a look at that and make sure your slopes are right. Make sure the slope for this graph represents what's happening with the velocity at any given point, and the velocity slope represents the acceleration. See you tomorrow.
Extreme physics.